worrying sometimes when I put a lot of expectations on.
2 weeks from Wednesday, we won't have school.
Okay. Hello, Kennedy. Hello, Spencer. Hello, Zane. Hello, Jared. Share for a minute and then I'll stop sharing it again. So normalization in first excited state is subject of today's meeting, and very soon we need to go to this set of subjects for presentations. I was almost panicking and thinking that if coming Wednesday we are not in the class, I was thinking how to replace it, but now we are safe. And we can present as early as coming Monday, or maybe delay a little bit, but as soon as we are done with the lab this Wednesday, I think everyone will be ready. And maybe on Wednesday lecture, we'll practice democracy with selecting whoever wants to do it. Those are just votes from previous year, and we get about the same thing, like covering several subjects until it's mine. Okay. So I've heard voices that this is quite easy homework that can be done by Friday. Let's plan on having it if anyone is against Friday, send me an email, because I'm not super inclined. We can, let's put double credit to everyone, to anyone who does it by Friday, and decide whether it will be, if everyone submits on Friday, then it will be double credit for everyone. If anyone wants to do later, I'll consider. So this whole work is not super challenging in either math or ideas. Yeah, I think it is doable by Friday. So it is a little supplemental math exercise that complement our main subject of the strawman walking up and down in energy, creation and annihilation operator. This is one of the excited states. I think it is number 3 without factors, and just practice how to draw functions. Should be easy. This is just taking derivatives, and by practicing derivative of higher order of the Gaussian function, then multiplying by Gaussian with, not Gaussian, but exponential with plus, this exponentials cancel, and then as a result, one is getting polynomial. Depending on what is the power, it will be different, like 1 minus x squared or stuff like that. Number 3 is very similar to what we do in class for creation and annihilation operator, but to make life easier, I'm trying to remove the constants. Otherwise, it is boring repeating of the same factors again and again. Here, just look back through the notes and tell something of the answer. It should be similar to the energy, but one needs to show it or make some comments. And the stuff here, give examples of harmonic oscillator. So in class, our first goal is to look on the interatomic distances in molecules, but this concept is much broader. There are a lot of things in chemical and physical world that oscillate, like radio waves. mass on a spring, and it's kind of competition who can give more examples. I think I can do at least 6 from the top of the head. Maybe someone can get more. Okay. So here is our little navigation map. On x-axis, we do have ideas and theoretical concepts. On y, we do have different models, and on z, it will be evaluation by external field. So we got evolution operator, time-dependent, time-independent Schrödinger equation, Schrödinger equation in matrix form, Heisenberg equation of motion density matrix, density of states and number of states, and last time we got ladder operator, which is a shortcut to replace eigenvalue problem for harmonic oscillator Schrödinger equation. At least it was motivation that no one my motivation that no one objected. And later on, this concept of ladder operator applied to harmonic oscillator can be quite generalized and specifically used for taking into account external perturbation when the molecule or material is probed by external, let's say, laser field. Okay, so few answers to the last question of the homework, which some of the class attendees will plan to complete by Friday. Different clouds, they don't have friction. Very strange feeling. Did you hear or did you read this word before? Librations. It sounds like library, but it has nothing to do with books. So, what happens if you dissolve polar molecule in a polar solid? Yeah. But what is the meaning of polar molecule?
As dipoles.
So positive, negative are separated in space. So it has its own dipole, its own electric field. What does it mean? We have polar solid. Each molecule of a solvent also has its dipole. Do they feel each other? Do they react to the fields of each other? Right?
Yep.
So if the solute molecule is very heavy and large dipole, and solvent molecules are small and have little dipoles, they kind of respond to the molecule, but it's both way traffic. So the dipoles of the solvent turn by the plus towards minus of the solute, and or by the minus to the plus of the solute, right? What happens if we heat the central molecule, or we heat it heated by heat, or heated by laser? It may start to let's say oscillate. But what will the solvent molecules do?
React to.
How? You can show it by your hands and fingers. Like there is a big molecule of a solute, and let's have fingers which are around. What they would do when the central molecule expands and contracts?
Follow it.
Huh? Yes, exactly, follow it, but in which way? Will the no, I'm not kidding, and there is no trap. There are 3 ways to follow. Follow like a dog follows the leash, so translate mechanically in space. Second, oscillate to contract and expand accordingly. And third, rotate, just as a compass to orient.
Rotate.
Perfect. So you know all the concepts here, yes. Speaking about, so it's I don't think we need much of sharing with these simple cartoons. I'll share again if there is a fine font that is hard to recognize through the camera. So when these solvent molecules follow the solute as little compasses, they can be formed forwards and backwards. So it is between rotations and oscillations. And the colloquial word is librations or vibrations. But it's also described as harmonic oscillator. Another thing, who of us doesn't have a cell phone? Raise hands. So no such people.
Doesn't have a
Cell phone.
oh,
So some people believe that I cannot use anything that I do not understand how it works. So how do your cell phones work? What's the main principle?
what
Call people?
Huh?
Yeah,
You
what
call people?
No, it's like a radio transmitter and radio receiver, first of all.
the phone part?
Yeah, so there are other additional functions, but main thing is the connection remotely without wires, right? So it's radio transmitter and radio receivers. So how does radio principle of sending out radio waves and accepting radio waves?
In the transmitter?
Yeah. So how to generate radio waves?
Electricity?
Yes, but if you have source of electricity as input and you need to have radio waves that someone will be able to detect, what is in between?
Transformer?
Absolutely correct. Perfect. I like it. But what is the details? What is the mechanism of this transformer?
Coil wire?
Yes. Only coiled wire or something else?
Something in the middle?
Uh-huh. And it is on the screen.
Capacitor?
Yes. So you guys are very sharp. You can design radio if you live like more than 100 years ago easily. So the source of the electric field are charges. So static charges give static electric field. If charges are moving, it is moving electric field. And if you want waves, it needs to be oscillating charges. But most efficient thing that energetically efficient and gives a higher output is a thing where charges oscillate naturally. And you already told everything. So you've told the word capacitor, which means you know what it is. So if you charge capacitor and then like very powerful capacitor and then take it by hands, it will discharge through you and you will feel a shock, right? If it is like micro picofarads, you will not feel it. But if you communicate enough charge to the capacitor and then short circuit, it will discharge through the circuit. Now, what happens with the coil? If you start pushing constant electric current through the coil.
Makes a magnetic field.
Exactly. So it will create magnetic field that will come through the center of this coil. But what would happen if you abruptly break the circuit, stop pushing electricity through? Will magnetic field immediately disappear or not?
Not right away.
Yeah, exactly. So it will have some inertia. And if you break the source circuit, but you connect measuring stuff like galvanometer, amperemeter, and you just measure, is there any current, is there any voltage, what is happening with this coil after you stop pushing current through it. It will show non-zero current because magnetic field created by moving charges is like inertia. So it is, it's you know, like in Eastern fairy tales, Aladdin, the creature that sits in the bottle. So magnetic field is like a creature that sits inside the coil. So even if you stop generating, it's still there, and it disappears slowly. While it disappears, changing magnetic field generates current. And the current will try to go through the coil even if you do not apply anything. So if you connect these two things, and they can work in the opposite phase, you charge the capacitor, then you connect it through the coil, it will discharge. While discharging, it will create magnetic field. And after everything is discharged on the capacitor, the current will keep going forward because magnetic field now shrinks and generates another current. And then capacitor charges in the opposite sign. And then when it's fully charged, there is no magnetic field, and it will try to discharge in the opposite direction. It will create magnetic field in the opposite direction, and then charge the capacitor in the opposite charge, and then it will go forward and backward. So such combination emits electric and magnetic fields which are periodic in space and time. And if you place such thing in the area with noticeable electromagnetic radiation, it will pull energy from radiation, from electromagnetic radiation, if the frequency of radiation is in the resonance with own frequency of this device. So both emitter and transmitter and receiver of radio waves are having this oscillatory circuit. And the math of this stuff is absolutely the same as for oscillating molecules or ball on a spring. So same equations and same solution, just oscillatory sines and cosines. And one can even quantize it and control it. Coil, capacitor, and there is an equation for frequency of the capacitance in the induction. So who we are and what are we doing? It is physical chemistry class. Originally, I was asking everyone to believe in that we are looking into the wavy nature of the electrons, and this will give us chance to describe some properties of molecules and materials. About a week ago, I changed my mind and told that not only waves of electrons matter, but one needs to take into account quantization of nuclear motion, which means interatomic distances and positions of ions also sometimes obey the quantum properties. Since, and I recently, previous slide, I gave a couple of examples, but our main goal as chemists is oscillations of ions, although there are some other things. And ions are oscillating near their equilibrium. Jared did help in setting Taylor series and telling that potential of the interaction between ions in the equilibrium can be taken just as x-squared function, right? And when we plug it into the Schrödinger equation, this kinetic potential energy, it is a differential equation that we need to solve. Or we want to find a bypass to get solution without solving equation, just to save maybe a few minutes or few hours. So second derivative, second power of independent function, eigenvalue, many functions, many eigenvalues. So our bypass is to practice again the Strawman that walks through the solutions. So we assume that solutions are known. There is a lowest energy solution, the next lowest, second lowest, and there is a way to go up and down by operators, ladder operators going up and down, or sometimes people use the word creation and annihilation, like creating more energetic state, annihilation getting down. And these states were chosen as superposition of position and momentum. Why? Because by going one step up and one step down, one returns to the same energy, which means product of these two operators is operator of energy. And energy is position squared and momentum squared with some constants. So we need to have first power in here, so that by multiplication we get the second power. So those have mass and frequency in the denominator and here in the denominator, and momentum is imaginary, and there is a plus and minus, so they are complex conjugate to each other. I cannot wait until I design a surprise quiz to memorize this stuff. I know it is challenging. I'm not remembering this in the middle of the night, but one day we need to try. So the goal is to, what was our main achievement last time? We decided philosophically, if that one tries to annihilate lowest state, one gets nothing, zero. And through this, we derive new equation. Just apply an annihilation operator to ground state, one gets zero. And this equation was solved. I want to believe it is here. So by solving this equation, it was linear equation, easy to solve, just integrating left and right part. And we found that the ground state of harmonic oscillator is Gaussian function, centered at the equilibrium, with widths depending inversely proportional to the frequency of mass and squared directly Planck constant in the denominator. So heavy mass will make very small width, which means one can neglect quantum effects. Light mass, larger width, which means one needs to take into account quantum effects. So from all ions, proton will have the like hydrogen. Ion will have the biggest contribution of quantum effects. If one wants chemistry of like materials for nuclear bombs like uranium and plutonium, then one can neglect quantum effects of their ionic motion. But we should be peaceful. Reactors for heat and electricity. Right. So what is missing here? We're missing the letter N, normalization, and we do not know yet if this trick will help us to get other set of states, like first excited, second excited, but we may try. And basically, so the goal is to find this normalization constant and find the first excited state. So at the end of whatever minutes we have, so in like 20 minutes, we should arrive to this equation, which will be the phi sub 1, first excited state. So it will be a product of the Gaussian bilinear function. And product of Gaussian bilinear, this one is always positive, and linear function is positive if R is bigger, extension, negative is if it is smaller, contraction. So it will be stuff like here, going up, going down, and then arriving to zero. If one takes absolute value square, it will be our favorite camel with two humps, same as in the one-dimensional walls. So things seems qualitatively correlated. Higher the energy, denser the fringes, in whatever system we consider. So in a few days, we can go and teach quantum photograph drawing camels. So we should get this equation by applying creation operator to the ground state wave function. If everything works well, we should arrive to this equation. I should retype it one day. So is it the same thing what Zane was explaining to Jared, or you were explaining some different normalization? Is it similar? So wave function multiplied by itself should give 1 because we are speaking about one particle. Now it is not an electron, it is like one interatomic distance. So we should find it somewhere with probability 1. Now, if we plug in the expression for phi sub naught, I think it is quite boring to look on pre-made stuff. So if the phi naught is normalization, E minus stuff, and then we need to, so it will be n squared, right? And then the power doubles. And after we integrate, we may want to manipulate the variables in such way so that the exponential will be in the power of one variable, because we know that integral of e to the minus variable squared will be square root of pi. So we need to bring it to this form. And in order to get these variables, we are going to multiply and divide the overall function by basically square root of this stuff to keep the same variable, right? So if we carefully do it, let me check if I typed it. Yeah, I think it's in typed form. Just screw with this. Looks like something important is skipped. So if we carefully change the variables, then we are getting integral of e to the power minus independent variable square root of pi, and this is our heritage from changing variables. So on the left we have one because it's our condition for normalization. On the right, we have n squared, which is unknown constant. And then we are solving for this normalization constant. So it is normalization constant square is square root of this stuff. So the h bar and m omega come from the power of exponential, and square root of pi comes from the integral of Gaussian function. And it is already a square root, but when we solve for n, we need to take square root of square root. So it should be power 1/4. So from now on, here this time, but we already. So we do have the normalization for the ground state, and and then we do have the solution. So we did check that integrating this function from minus to plus infinity will give 1. So it is normalized to a function that can be used for finding observables and expectation values. We did obtain it by applying annihilation operator to the unknown, to this unknown function, to the ground state. And from now on, we do believe that by applying creation operator to this function, we should get the first excited state. So we are, I don't know, do you think this image is confusing or it is natural? So the x-axis is elongation of the bond. Y-axis is kind of wave function absolute value squared plus energy, right? So they are offset. And if here we have our ground state, then here will be our first state. So we are applying creation operator to the ground state, and we hope that it will be state number 1. So I'm not yet ready to give the quiz because I don't remember the things from the top of my head myself. But let's try to reproduce it, and then I'll look into my cheat sheet. So what I remember that there were square roots here and there, and in front of position, frequency and mass were in the denominator. In front of the momentum, it was in the denominator. And there was Planck constant here and there, and I think maybe there was factor 2. So there is a way to check if it is correct. Is multiply conjugated operator of creator and annihilator and check if we are getting energy. It just will take time. So I hope that on my next slide I will have a cheat sheet and the exact values to check if these constants are right. And what we are going to do is to replace momentum with its definition. And then we will multiply our ground state function by position and take derivative. So which is kind of trivial, but one needs to take care of the factors. Okay. So I believe that I took the square root of product of mass frequency and Planck constant out of brackets. So if so, basically everything that was in front of momentum can be taken out of brackets, and then in front of the position it will be no square roots, just mass and frequency. Okay, and then I plug in the definition of momentum, and through this operation, I'm getting rid of the imaginary unit in the second term. This is okay. So we look at mass, frequency, and position, and we have the Planck constant and derivative. And we need to apply it to this exponential, this square, minus square of elongation and the factors. So in the first term, we are just getting a product. In the second term, I am applying the derivative to the exponential, and as a price of this derivative, I'm getting the factor in front of independent variable, so mass, frequency, Planck constant, and then taking derivative of the r squared function, I'm getting 2r in front of it. So if one looks carefully into what is going on here, the Planck constant and factor 2 are cancelled. Okay? And we are getting mass times frequency in both terms. Here you get independent variable r, and here we have independent variable r. And by taking derivative, we have additional minus here, which compensate this minus. So we basically have two identical terms, and they are added together. Right? So we just add factor 2, and if we do not care about factors, it is the exponential times linear. So multiplying Gaussian by linear will be positive, or elongation is positive, will be negative, or it is negative, and you have that stuff. I think we did arrive where we wanted to arrive, and I think it is enough for today. So, whereas Monday and Tuesday, I'm looking forward to see you on Monday. Quickly check if everyone already left. So here's my favorite thing.